And today I'm going to be talking about igniting a fusion energy future with optics and photonics. There's been quite a few talks touching on the importance of energy, both the role of glass in energy and energy in the production of glass. And so we know that energy is one of the most vital resources that keeps our modern world running. But here's the thing, we know that worldwide energy consumption is projected to increase 33% by the year 2040. So in less than 20 years from now, we have to find a way to produce 33% more energy than we use today. It's instructive to take a look at how we meet those energy needs. Certainly, there is solar and there is wind, renewable, clean energies. However, they constitute less than 25% of our energy supply today. And for the most part, we are still reliant on coal, oil, and natural gas. And of course, we all know that coal, oil, and natural gas are carbon sources contributing to global warming and climate change. So the question is, could we build a miniature sun here on Earth to provide significant carbon-free energy for humankind? And you've heard a little bit about this today, that the sun and the stars are powered by fusion. And the idea behind fusion is, of course, very simple. You are going to slam two light ions together. And in our case, we are interested in deuterium and tritium, isotopes of hydrogen, that if you get your plasma hot enough and dense enough, they will fuse. And out comes a helium nucleus or an alpha particle, and a neutron, and a huge amount of energy. Why is that? Well, we're really using an equation that we all know very well, equals mc squared. If you weigh your deuterium and tritium before your reaction, they weigh a certain amount. Through the fusion process, your products on the other end weigh a little bit less. And that little bit of liberated mass goes into Einstein's equation as your m. You multiply by the speed of light, c, a really big number squared, and you get a huge amount of energy out. And so you see that there's a huge amount of potential in fusion. Now, where do we find our hydrogen fuel? Well, it really is that water, H2O, is the fuel of life. Deuterium is naturally occurring in seawater at 1 in every 10,000 particles. Tritium, we have to breed from lithium, but we know how to do that quite well. And so, it turns out that fusion fuel is actually very plentiful. A single pound of fusion fuel is equivalent to the amount of energy in 5,000 barrels of oil, or 3.5 million pounds of coal. So potentially, in seawater alone, we have enough fusion fuel for 30 million years. And so fusion energy is actually attractive for many reasons. First of all, it is safe. It's actually quite hard to get fusion going. You need an energetic driver to deliver energy into your system. So if you ever want to stop a fusion reaction, you just turn off that initial energy source. You don't have to worry about runaway like you might with fission. It is carbon-free. You could see in that reaction, our only byproduct was helium and neutrons. It is sustainable. We know how to obtain the fusion fuel that we need without damaging the environment. Baseload. It's envisioned that a fusion power plant would be a gigawatt scale plant, kind of the size of our large scale coal plants today. And fusion is an on-demand energy source, meaning that you could provide the energy that you need when you need it. And it can be varied as a function of your population's needs. There's no geologic storage, there's no high-level nuclear waste associated with fusion. And if we can demonstrate fusion to be a viable energy source, no longer will we be reliant on foreign oil imports. So it leads to energy security, sovereignty, and diversification. So at the National Ignition Facility, the NIF at Lawrence Livermore National Labs, which is about 60 miles east of San Francisco, we are building our own miniature sun. The NIF is the world's largest and most energetic laser, which enables us to study very extreme conditions for our field called high energy density science. You can see the laser is housed in a football stadium-sized facility, 3 football fields side by side, 10 stories tall, and of course I picked our favorite California team and display on there. It's actually 192 separate lasers. Each one alone is one of the most energetic in the world, for a total energy of 1.9 megajoules. The power output is 500 terawatts. That is 1,000 times the power of the US electrical grid. So how come your lights don't flicker every time we take a shot? Well, we're gonna take all that laser energy and compress it into a very small amount of time, about 25 nanoseconds. For the laser aficionados out there, this is frequency tripled neodymium glass at a wavelength of 351 nanometers. And if I take excuse me, the roof off of the facility to give you a look inside, you can see that the majority of the building is actually taken up by amplifying optics, which amplify each of these lasers up to over 10 kilojoules before all of that laser energy is focused back down onto our tiny target that's about 1 millimeter cubed in size. So right here is the fuel pellet that's going to contain your deuterium tritium, about 2 millimeters in diameter, sitting in the middle of this canister that we call a hole ROM. The NIF is the world's largest optical system, containing over 7,000 large optics. These optics include amplifier slabs, mirrors and polarizers, windows and lenses, crystals, and debris shields. And each of these optics must meet stringent optical requirements, have very high resistance to laser damage, and be manufactured to be over 0.5 meter in size. And so you see here, here's a couple of examples. These are our KDP crystals, potassium diphosphate, that we use to frequency triple the laser light. This is the laser phosphate glass that is our amplifying medium. Here's a fused silica optic that could be a lens, could be a mirror, and then borosilicate glass here shown as the front face of our deformable mirror that we use to make sure that the wavefront of the laser is as uniform as possible. So why do we have such a complex system? Well, what we're going to try to do is inertial confinement fusion to bring star power to Earth. But whereas the sun is 1 million miles across, what we're going to do in the laboratory is create miniature stars on the order of 2 1,000ths of an inch, about half the diameter of a human hair. And like I mentioned before, the NIF is going to use what we call a laser-driven hole ROM to compress that fuel pellet of deuterium and tritium to achieve those conditions for ignition. The hole ROM is a cylindrical cavity. It's a tiny itty-bitty soup can, I guess, with 2 holes on either end, about 1 centimeter in length, 0.5 centimeter in diameter, typically made of a very high Z element, gold or depleted uranium, for very efficient conversion of laser energy into X-rays. So what we're going to do is bring half our laser beams in through the top laser entrance hole, half through the bottom. They hit the inside wall, generating a very energetic flux of X-rays, and those X-rays will compress the fuel capsule that sits right in the middle. The fuel capsule consists of a plastic, or in some cases, high-density carbon, which is a more palatable word than diamond, but it is a diamond ablator, surrounding our fuel, which consists of DT ice and DT gas. You want the gas so that your capsule is compressible. However, we have to pack enough fuel in there, so we do grow the deuterium tritium ice layer, just like water ice, but pure deuterium tritium. And the trick of inertial confinement fusion is to turn 100 million atmospheres of photon pressure into 300 billion atmospheres of pressure via spherical convergence. And the challenge is to try to do your a convergence that is as symmetric as possible, so that you get to a round hotspot where you can now generate propagating fusion burn. So I'm going to play you a little video to show you how all of this comes together. There is going to be a little bit of background music that I'm going to talk over. So we start in the NIF control room. If I can turn up the volume just a little bit. And you can see that the NIF control room is modeled on the NASA control room, where we control most of the subsystems of NIF remotely. So first, the laser is going to be born in the master oscillator room at a nanojoule level. That's okay, I'm going to keep talking. Where it is going to be shaped in time. It's a fiber laser that generates the initial pulse. The laser gets split 48 ways and goes into the preamplifier module, thank you, where it's going to bounce around about 100 times, getting amplified up to the millijoule level. Now, each of the beams gets split another 4 ways, goes into the main amplifier, where it's going to bounce 4 times back and forth across that enormous facility that I showed you. At this point, we're going to start following the beam path with a single laser, and you can see now that each laser is a square, about 40 centimeters by 40 centimeters in size. And the reason the laser is so large is because we need to spread that laser energy out so as not to damage the optics as they're traveling through. The lasers are now going to approach the target chamber that sits right there in the middle, 10 meters in diameter. Half our laser beams get sent up, half get sent down. They're going to sync up in time, and we're going to frequency convert from red to green to UV. And now all 192 beams are going to be incident on that tiny target that sits right in the middle. Half the beams coming in through the top, half through the bottom. They're irradiating that inside wall, generating an X-ray of about X-ray flux of about 300 eV Planckian. Those X-rays start ablating the outside surface of the capsule, which by conservation of momentum drives the rest of the capsule inwards. And if we do it just right, we get that capsule really hot, really dense, and we have ignition. More energy out than we put in with the lasers. And our facility itself is a superstar itself. The NIF was the set for Star Trek Into Darkness, which was filmed in 2013. You can imagine some of the reviews we had to go through with DOE to allow this. But our warp core, our target chamber served as the warp core for the Starship Enterprise, and it was a very exciting month for some of the nerds that we had. Okay. So we started experiments on the NIF when it was completed in 2009. And the question is, how close are we now to actually demonstrating ignition? How close are we to making fusion energy a reality? Well, if you think about the challenge of ignition as a mountain that we have to climb, our y-axis is going to be the energy produced. You can think of it as the elevation of the mountain that we have to climb. This is actually going to be a scientifically accurate plot that I'm going to show you, where our x-axis is the Lawson criterion for fusion. It's a parameter that folds in the temperature of your plasma, the density of your plasma, and the confinement time. So how long you can hold your plasma together to actually give it time to fuse. Well, before the NIF was built, at Livermore, our previous laser was the NOVA laser, and at that time we were about 10,000 feet away from the top of the mountain. We were at the base. When the NIF came online in 2009, our first experiments, we found that we were about 100 feet away from the top, 100x. We still had to couple 100 times more energy into the field than we were doing at that time. By 2012, we had made significant learning and improvements, and we were 10x away from where we needed to be. By 2015, we had found ways to control the hydrodynamic instabilities to some extent, have a more stable implosion, and we were 3x away from where we needed to be. And at that point, we actually demonstrated what we call alpha heating, meaning we were able to trap enough alpha particles, those helium nuclei, that they could redeposit their energy and help with the fusion burn. By 2018, we were 2x away. We reached a burning plasma at that point, so a robust plasma that could feed back on itself. And then, of August 8th of last year, we achieved 1.35 megajoules of fusion yield, where we had 1.9 megajoules of laser going in. So this was about 70% of energy gain. Where ignition would be if we got more energy out than we put in with our lasers. So we are almost there to demonstrating ignition. It was a very exciting day in the life of a physicist. There's not that many of those. We got a lot of very exciting press heralding the result, and immediately extrapolating to the idea of fusion energy and the potential it provides. But I do want to say that fusion energy will be a multi-decadal endeavor. It will not be easy. Even after we demonstrate fusion gain, that is solving the physics problem, there is still so much engineering and technology advancements that we need. Many of them will include building better lasers, faster lasers, and we'll obviously need a lot of optics and photonics advancements there as well. However, this is a grand challenge of science, engineering, and technology. And it is something that we are very excited to help bring new students into the field with, something that will spur innovations in multiple fields. And so we are working with the US government and private industry now to try to grow this into a robust, vibrant field. And another reason I'm so excited about inertial fusion energy is because Livermore has been delivering leading-edge laser and optics solutions for over 50 years. And I know this slide is hard to see from the back, but here we list just some of our laser firsts at Livermore, including the mercury laser, which was the world's highest average power 10 hertz laser. We're currently working on the DPAL laser for the Department of Defense. It is a very high average power laser, so high I can't even tell you. Nova Petawatt was the world's highest peak power laser, et cetera, et cetera. So it's a very exciting place for me to get to work at. So I'll just wrap up that achieving ignition on the NIF will bring us closer to harnessing the energy of the sun and stars to meet the Earth's energy needs. Thank you.